This is Nitin Dahad with the Times. I'm visiting the National Quantum Computing Centre in the UK, in the middle of the UK actually, and talking to Scott Dufferwiel, who's the co-founder of a company called Aegiq. Scott, hello.
Hello, Nitin. Pleasure to be here. Nice to meet you.
Well, thanks for showing me what you're doing here. But tell me just a little bit before we go into what exactly is happening here. What is Aegiq? It's a startup which you co-founded in 2019, coming out of some research at the University of Sheffield. Is that right?
Yeah, that's correct. So Aegiq was co-founded in 2019. We started based on a technology developed over 20 years at the University of Sheffield, and we focused on building scalable photonic quantum computing systems.
That's quite a very generic statement. So tell me, the photonic quantum computing system, that in itself needs an explanation, and then scalable, I think, is quite important. But before we go into that, and I think you'll explain it in doing that, but what are the big challenges in quantum computing right now? What do you think is missing, and this is where you thought is something you can do?
Yeah, absolutely. So I think in quantum technology, what we're seeing at the moment is a huge amount of investment in the sector, and this is leading to a huge amount of development in terms of technological capability. Now, the way we view it is that what we need to get to is systems that can deliver commercial value, and that means large systems, 1 million qubits to be able to deliver the capability you need to solve useful problems. There are many different approaches to do this, many different modalities, and our view is that many of these modalities, due to the early design choices, are going to hit a ceiling of performance that's not going to allow us to scale to the level that we need to. Now, our approach here is to use photonic-based systems. If you need 1 million qubits, or 1 million things of any kind of technology, there are kind of two ways to go around this. One is to use the semiconductor industry, similar to how you've got transistors in your phone seamlessly operating to deliver compute, or you can look for the optical networking capability, the backbone of the fiber optic systems around the world, millions of systems synchronized and operating unanimously. And what we're doing is combining the best of those two things. We're taking scalable semiconductor chips, interconnecting them with optical fiber to provide a clear pathway where we can break through this ceiling of performance and deliver the capability needed for commercial applications of the technology.
And actually, you've developed a system, a modular system here, which we've come to see here at the National Quantum Computing Centre. We're part of this here. So just walk us through the system. It's 4 pillars.
Yeah, absolutely. So
what 3 modules here, but 4 pillars. Yeah.
So the way we kind of view these systems as our computers look very much different to others. We don't involve chandeliers. There's no extreme environments. For us, it's around scalability, and that means on-premises deployment. So everything's in a 19-inch rack. Yeah. And this is intentional. I mean, the most exciting thing is it's a white rack, not a black rack, but this can be seamlessly deployed in a data center. Yeah. And then sitting in these kind of modules, all these optical fibers connecting, is a set of semiconductor chips that we like to talk about in terms of 4 pillars. The first, on my right-hand side, sitting in this rack, is a single-photon source. So we use a compound semiconductor technology developed over 20 years and 24 PhDs at the University of Sheffield. Essentially what we can do is we can press a button and emit photons on demand. And this is kind of the engine behind the system.
Single photons on demand.
Single photons at the moment. Okay. And what we do with those single photons is that we then go to the second pillar, which is a switching system, and when we can fire them around the unit. Similar to what you see in an optical network, but basically we can take a very fast stream of single photons, or our qubits, and ballistically move them around the system. And as they come out the other side, we then put them into a silicon chip. And this silicon chip is really kind of the heart of the system. If the source is the engine, this is the QPU and this is the heart.
That's the QPU down there.
Sitting in the bottom. And we work with some partners in the Netherlands to develop a system based on kind of ultra-low loss silicon nitride. And on that, we have 380 tunable parameters. We can move the photons around the system. We can switch them. We can interact them. We can entangle them. And when the user engages with our system, what they're really doing is we're changing that QPU unit to encode an algorithm, and then what comes out the other side is kind of photons that have been encoded in, and then we read out. And readout is in this system here in the middle pillar, and this is superconducting detectors. We can measure single photons, and we've got 20 chips inside of this system, each reading out the photons. And collectively what this creates is an optical network of semiconductor chips, but a functional photonic quantum computer. At the moment we're looking at between 4 and 6 qubits flying through the system.
Okay, and the key thing also, I think, when you did the demo earlier is you don't need to know all the internal bits. You can access it through Python.
Yeah, absolutely. So we're a full stack company. We work on applications with end users, and then we work on the hardware, and in between develop all the software, low level, middleware and above, so that an end user can abstract what they want to do from the details of basically transistor logic equivalent on the QPU. So what we have is a full Python interface called our Lightworks SDK, and that allows an end user to develop a algorithmic system, deploy it on a hosted server and deploy it on the system. So an end user over in the NQCC applications team, they don't need to come to the lab. They just log onto their computer, write their jobs, submit it, and receive the jobs in the same way you would leverage an AWS HPC system.
All right, let's go to that now. So NQCC is one of your customers. What are you seeing being done at the moment with your system? You've got a couple of deployments in already.
Yeah, so the system's kind of all fully commissioned. It's been here since the end of May. And what we're doing now is basically just improving the performance, iterating, kind of greasing the wheels a little bit to get the maximum from this. From September, we'll be doing verification and verification and assessment of certain approaches. We're working with the Quantum Software Lab up in Edinburgh to deploy and test these systems. And in parallel, what we're interested in is very much the early stage proof of concepts that we can show will allow us to build systems that are larger to solve useful problems, but to be able to do POCs in the meantime to show that you can demonstrate the capability to get there.
And how do you scale this? I mean, one of the things I think you talked about is going to 1 million qubits. How's this different to what else is out there, or what approaches are out there? And I know it's very hard because everything is in very development stage at the moment. So how's this different?
Yeah, so I mean, there's many different modalities.
Yeah.
People are backing all sorts of different approaches. We like to call these flying qubits photons, and photons are very different to all the more mature approaches, which are kind of static. So your superconducting, your atoms, your ions. Our approach is slightly different. So with those modalities, it's really about building small chips with very high performance, trying to get super high fidelities, connectivity, and demonstrate these on these small chips, and then scale them once that's been achieved. We're inverting that problem. At the heart of photonics, it's all about scalability from the start. What we want to do is build a system where we can leverage the semiconductor industry, interconnectivity, and scale out via optical connections between modules, and build a system that allows us to leverage what's already in place from a manufacturing perspective. So all of our chips are compound semiconductor based or the silicon photonics based. And really, it's kind of tackling the big engineering challenges up front so that scalability comes naturally. And I would perhaps say that some of the other modalities are trying to build very small scale demonstrator systems and going to address scalability later. But for us, the path towards useful applications, it's 1 million qubits, which means we have to have a clear route to get there at the fastest pace to be able to deliver value.
How big would that be then? It'd be quite much bigger than this, I guess.
It'd be a little bit bigger than this. Lots of miniaturization to be done. We imagine that a large scale system will be the order of a few lines of racks. Okay. So it'll be data center compatible, on-premises compatible, no big cryogenics extreme environments, but it won't scale completely in line with this. We expect miniaturization as we start bringing the technologies together.
So at the moment, you're selling these modules to, I think, existing, like 2 customers you have.
Yep.
But ultimately, this will be, as a business model, you'll be able to access it via the cloud, or will you have on-prem?
So it's a good question. A little bit of both. I would say that at the moment that you can access quantum computing as a service from many providers. For us, it's a little bit early. We prefer the on-premises application of this technology because photonics naturally allows itself to have simple modules where you can put it outside of a lab and into a data center for an on-premises deployment. So there's a natural ability to put photonics in the heart of customers. Longer term, I think as technology matures, you'll see an admixture of both, where you have some on-premises deployments and some accessibility in the cloud. But I think the key aspect related to all of this is a technology that will sit adjacent to current technologies, CPUs,
GPUs, etc.
Exactly, and you need to leverage that infrastructure to get that into the hands of customers.
You said TTL earlier, you have QQL as well, I guess.
Exactly, exactly. Yeah.
And now, from a business point of view, company point of view, you're what, 25 people, is that right?
Yeah, we're 25 people. We're headquartered in Sheffield, so we're still based where we spun out of. And we're staying up there primarily because we have a very good relationship with the ecosystem already developed, and we work very closely with National Epitaxy Facility.
And you work with IQE as well, Foundry as well?
Yeah, so this was funded via the UK government's quantum testbed program, working with the NQCC. We received a quantum mission pilot funding, and really that's about scaling our technology. So we're basically moving our source technology into a 3.5 foundry, and we're currently working with IQE to scale that towards large-scale, large wafer manufacture. We don't care about volume, we care about uniformity, reliability, and reproducibility, and we'll only get that from a tier 1 foundry partner.
And in terms of that path, I mean, at the moment you've raised about 15 million.
So 8 million equity and the rest combination of grants and direct contracts.
And these are investors UK, Europe, and US?
Yeah, primarily UK, Europe, and some US investment, yes.
Okay. So what's next for you? What's your plan? What's your roadmap?
So we have a 5-year accelerated plan. We're currently building our relationship with our foundry partners to scale to build better systems. And what we mean by better systems is to get to the point where we can deliver systems, deliver commercial value. We're doing this over 3 generations of quantum compute. This is generation 1. Generation 2 around 27, 28 is to basically build out the capability so that we have a blueprint that we can scale. And around 2030, we want to be able to put this into a small facility where we can deliver what we call utility scale, where you can solve useful problems with the capability on the system. And to do that, we'll be going to market later this year for our Series A round.
Well, Scott, thank you very much.
Thank you very much, Nitin.
Thank you.